Hello guys, in this video I'll be talking about NMR spectroscopy from the Clayden book. So previously I have made 3 or 4 videos regarding NMR spectroscopy where I have discussed the basic definitions and fundamentals of NMR spectroscopy. But in this talk I'll be talking about coupling in the proton NMR spectroscopy. So what is coupling and what are the factors that we should look for the coupling? And nearby hydrogen nuclei interact and give multiple peaks. So you often see that in NMR sometimes you see a singlet like this, and sometimes you see a doublet like this, and sometimes you see a triplet like this, or sometimes you see a quadruplet like this. Okay, so why we have multiple peaks or multiplicity in the NMR spectrum? Because of the presence of the coupling. So coupling is called interacting with hydrogen nuclei. So far proton NMR has been not unlike carbon NMR on a smaller scale. However, we have yet to discuss the real strength of proton NMR, something more important than chemical shifts, and that is coupling constant. Something that allows us to look not just at individual atoms but also at the way CH skeleton is joined together. This is the result of interaction, that is important, between nearby protons known as coupling. Okay, an example we could have chosen is in the last section. So I'm reading these lines from the Clayden book. Okay, so we have chosen is the nucleic acid component cytosine, which has exchanging NH2 and NH protons, giving a peak for HDO and at 4.5 ppm. We didn't choose this example because other two peaks would have puzzled you. Instead of giving just one line each, they give 2 lines each. Doublets. So doublets is 2 lines, so we write doublets as small d and we write them as like this. Okay, as you will learn to call them, and it is time to discuss the origins of the coupling. Okay, cytosine is one of the 4 bases that is in combination with deoxyribose and phosphates make up DNA. It is a member of the class of heterocycles called pyrimidines. We come back to the chemistry of DNA towards the end of this book, that is in chapter 49. That in that chapter I'll be discussing about DNA and RNA and the nucleic acids and the base pairs. Okay, so but here we are just limiting ourselves to this topic about NMR. So if you look at this compound here now, this is a pyrimidine base, and that is NH2 and this is NH. So this HA and HX, they couple to each other and they give you the multiple peaks. So for example, this is the orange signal is for HA, which gives you the doublet, because this HA is coupling with the HX, and this signal is for the HX, which is coupling with the HA. Hence, so this HX couples with HA to give you the doublet, and then this HA couples with HX to give you the doublet. This is the D for doublet of HA, and this is the D for doublet of HX, and this is the proton NMR at 6 megahertz, and this is how we write proton NMR, and the solvent that we have used is D2O. And now let's have a look at the other examples, then we will find out the more details about this. You might have expected a spectrum like that of the heterocyclic bellow, which is also a pyrimidine. It too has exchanging NH2 protons and 2 protons on the heterocyclic ring, but these 2 protons give the expected 2 lines instead of the 4 lines in the cytosine spectrum. It is easy to assign the spectrum. HA is attached to an aldehydic C double bond N, and so comes at lowest field. The proton HX is ortho to 2 electron donating NH2 groups, and so comes at high field for an aromatic proton. These protons do not couple with each other because they are too far apart, they are separated by 5 bonds, where the rings proton in cytosine are separated by just 3 bonds. So if you look at the bond distance between this HX and HA, now it's 1 bond, this is 2 bond, 3 bond, 4 bond, and 5 bond. Now the HA gives you the singlet, and HX also gives you the singlet, because they cannot couple with each other. Why? Because the distance between the 2 atoms is quite big, quite large. That's the reason why they cannot couple to each other. And this is the peak for HOD. Why HOD? Because this is the remaining solvent peak from the D2O. Understanding this phenomena is so important that we are going to explain it in 3 different ways. You choose which appeals to you most. Each method offers a different insight. The pyrimidine spectrum has 2 single lines. That's what we call singlets. We shall call them from now on as singlets, because each proton HA or HX can be aligned either with or against the applied magnetic field. The cytosine spectrum is different because each proton, say HA, is near enough to experience the small magnetic field of the other proton HX, as well as the field of the magnetic field itself. The diagram shows the result. Now if you look at this is HA and this is HX spectrum with no interaction. Okay, now this peak is 7.5 ppm and this peak is at 5.8 ppm. So effect of HX and applied field acting together on HA. This is the applied field and this is the HA, and HX aligned with the applied field. Okay, so they are applied in the field direction of the applied field. And now if you look at this thing here, effect of HX and applied field acting in a position on HA, this is in the opposite direction and this is the aligned direction. Effect of HX on HA and HA on HX. So a resultant spectrum is this, doublet and doublet. And if each proton interacted only with the applied field, we would get 2 singlets. But proton HA actually experiences 2 slightly different fields, the applied plus the field of HX or the applied field minus the field of HX. HX acts either to increase or to decrease the field experienced by HA. The position of a resonance depends on the field experienced by the protons, so these 2 situations give rise to 2 slightly different peaks, a doublet, as well as we shall call it, and whatever happens to HA happens to HX as well as. So the spectrum has 2 doublets, one for each proton, each couples with the other. The field of a proton is a very small indeed in comparison with the field of the magnet, and the separation between the lines of a doublet is very small. We shall discuss the size of the coupling later. The second explanation takes into the account the energy levels of the nucleus. In chapter 4 of this Clayden book, when we discussed the chemical bonds, we imagined electronic energy levels on neighboring atoms interacting with each other and splitting to produce new molecular energy levels, some higher in energy and some lower in energy than the original atomic levels. When the hydrogen nuclei are near each other in the molecule, the nuclear energy levels also interact and split to produce new energy levels. If a single hydrogen nucleus interacts with a magnetic field, we have the picture. This chapter, there are 2 energy levels, as the nucleus can be aligned with or against the applied magnetic field. There is no energy jump possible, and there is a resonance at one frequency. This you have now seen many times, and it can be summarized as shown below. So this is the energy levels for an isolated nucleus HA. So this is the energy and this is the applied magnetic field on this direction, applied magnetic field, and that is the energy. Now high energy level, and this is the lower energy. Nucleus A aligned magnetic field, aligned with magnetic field, and nucleus A aligned magnetic field. The spectrum of the pyridine showed two protons which independently in this situation. Each had two energy levels. Each gave a singlet, and there were two lines in the spectrum. But in the cytosine molecule, each proton has another hydrogen nucleus nearby, and there are now four energy levels. Each nucleus HA and HX can be aligned with or against the applied field. There is one most stable energy level where they are both aligned with the field, and one at least stable where they are both aligned against. In between, there are two different energy levels in which one nucleus is aligned with the field and one against. Exciting HA from alignment to alignment against the applied field can be done in two slightly different ways, shown as A1 and A2 on the diagram. The result is two resonances very close together in the spectrum. And applied magnetic B field B naught, and this is the energy levels for two interacting nuclei HA and HX. And if you look at this A, both nuclei A and X aligned with applied magnetic field, and this A1 energy required to excite A against X and against B naught, and this one is nucleus A aligned against applied magnetic field, as you can see here, while the X is aligned with the magnetic field. These have slightly different energies, and nucleus A aligned with the applied magnetic field again, and X is aligned against the magnetic field. So please notice carefully that we cannot have this discussion about HA without discussing HX in the same way. If there are two slightly different energy jumps to excite HA, there must also be two slightly different energy jumps to excite HX. The difference between A1 and A2 is exactly the same as the difference between X1 and X2. Each proton now gives two lines. Each proton now gives two lines a doublet and in the NMR spectrum, and the splitting of the two doublets is exactly the same. We describe this situation as coupling. We say A and X are coupled, or X is coupled to A, vice versa. Of course, we shall be using this language from now on, so must you. Now look back at the spectrum of cytosine at the beginning of this section. You can see the two doublets, one for each of the two protons of the aromatic ring. Each is split by the same amount. This is easy to check with a ruler, and the separation of the lines is called the coupling constant. And it's called J. In this case, J is 4 Hz. Why do we measure J in Hz and not in ppm? We measure chemical shifts in ppm because we get the same number regardless of the rating of the NMR machine in mHz. We measure J in Hz because we also get the same number regardless of the machine. Okay, and now if you look at this, there is a distance between these two lines that is called the coupling constant, and the coupling constant for this doublet is 8.8 Hz, and the coupling constant for these two lines is 8.8 Hz, and the coupling constant between these two lines is 12.3 Hz. And the coupling constant between these two lines is 12.3. Spectrum recorded on 90 MHz, but if you record this spectrum on 300 MHz, the coupling constant is same. Coupling constant is independent of the instrument, okay? So it doesn't matter which instrument we are using. Now let's move on. So measuring coupling constant in Hertz. To measure a coupling constant, it is essential to know the rating of the NMR machine in megahertz. This is why you are told that each illustrated spectrum is say at 250 megahertz. To measure the coupling, measure the distance between the lines by a ruler or divider and use the horizontal scale to find out the separation in ppm. The conversion is then easy. To turn parts per million of megahertz into hertz, you just leave out the million. So 1 ppm on a 300 megahertz is 300 hertz. On a 90 megahertz machine, it would be 90 hertz. spectra from different machines. When you change from one machine to another, say from 80 MHz to a 500 MHz machine, chemical shift stay the same in ppm, but coupling constant stay the same in hertz. Now for the third way to describe coupling, if you look again what the spectrum would be like without interaction between HA and HX, you would see this with the chemical shift of each proton clearly obvious. So this is HA, spectrum of molecule without coupling constant, that is a single line, and this is HX without decoupling, it's a singlet. And now next is this one, two protons couple. This is how they couple between this HA couples with HX, and this is called JAX because J is for the coupling and AX for A is coupling with X, and this 4 Hz is the distance between these two lines, while this is HX and this is called JXA, while J is for the coupling constant, XA is X is coupling with A, and the distance between these two lines is 4 Hz. But you don't see this because each proton couples with other and splits its signal by an equal amount either side of the true chemical shift. Spectrum with coupling. So this is the ppm value for A, 7.5 ppm, and the distance between these two doublets is 4 Hz. So J is called coupling, the A couples with X, that is 4 Hz, and this is coupling constant for signal X, 5.8 ppm, and that is the distance between these two lines, JXA. X is the proton which couples with A, and the distance between X and A is 4 Hz. So this spectrum would be described as chemical shift at 7.5 ppm, 1 proton doublet J 4 Hz HA, and 5.8 1 proton doublet J 4 Hz HX. The main number gives the chemical shift in ppm, and then in brackets comes the integration as the number of Hs. The shape of the signal here D for doublet, the size of the coupling constants in Hz, and the assignments usually related to a diagram. The integration refers to the combined integral of both peaks in the doublet. If the doublet is exactly symmetrical, each peak integrates to a half proton. The combined signal, however complicated, integrates to the right number of protons. We have described these protons as A and X with a purpose in mind. A spectrum of two equal doublets is called an AX spectrum. A is always the proton you are discussing, and X is a proton with a very different chemical shift. If the difference of chemical shift between two protons is very large, then we call this system is AX. If there are more protons involved, a splitting process continues. Here in the NMR spectrum of a famous perfumery compound supposed to have smell of green leaf lilac, and the compound is an acetal with 5 nearly identical aromatic protons at the normal benzene position 7.2 to 7.3 ppm and 6 protons on 2 identical OMe groups. So this is the HX, this one is HX, and this is HA. These are the two OMe, and this is the 90 megahertz. So we have this HA, it's a triplet, and this is the HX, it's a doublet because these are the two lines, that's why we are calling doublet, and there are 3 lines because HA couples with these 2 hydrogens to give you the triplet, and we write triplet as T, and HX couples with HX couples with HA, that's what we call it D. And this is also HX, the doublet, and this is the expansion of this signal, and this is the expansion of this signal. It is the remaining 3 protons that interest us. They appear as a 2H doublet at 2.9 ppm, and 1H triplet at 4.6 ppm. In NMR, in NMR talk, triplet means 3 equally spaced lines in the ratio 1:2:1, that is for the triplet. Triplet arises from 3 possible states of the 2 identical protons in the CH2 group. If one proton HA interacts with 2 protons HX, it can experience 3 states of proton HX. Both protons HX can be aligned with the magnet or both against. These states will increase or decrease in the applied field just as before. So in other words, for the triplet, the intensity ratio is 1:2:1. So again, here is the HA and this is 2HX. So HA appears at 4.6. Spectrum with no interaction will be like a singlets, and when they will interact, then they will look like this. So HX will give you a doublet and HA will give you the triplet. We could conclude that the triplet is of this intensity 1:2:1, and 2 states of HA. 1A is aligned against the magnetic field, A is aligned against the magnetic field. So 3 states of 2H, X1 and X2, they are aligned against. X1 and X2, they are aligned, and one is aligned, one is against, and another is aligned. So this is how you do the coupling in an AX2 system. So HA couples with X, it gives you the doublet, the coupling to first HX, and then this A couples with another HX, it gives you the triplet. So final thing, that is the triplet. So HA, 2HX couples with HA to give you the 2 lines. That's why we are here a doublet, and that's why we have here is a triplet. That's the AX2. So constructing the Pascal's triangle, put 1 at the top and then add an extra number in each line by adding together the numbers on either side of the new number. In the line above, if there is no number on one side, that counts as a 0. So the lines always begin and end with 1. So this is the Pascal's triangle. So for singlet, it's 1, and we call singlet as S. We call doublet as D, and we call triplet as T. We call quartet as Q, quintet, sextuplet, septuplet. Number of neighbors. In singlet, there's no number of neighbors. In doublets, number of neighbors is 1. In triplets, number of neighbors is 2. In quartet, number of neighbors is 3. In quintet, number of neighbors is 4. In sextuplet, 5, and septuplet, 6. Moreover, in singlet, we have the 1 line. That's why we write it 1. And for doublet, ratio is 1:1. And for triplet, it is 1:2:1. And for quartet, it is 1:3:3:1. And for quintet, it's 1:4:1, 4:6, and 6:4, and 4:1. And for sextuplet, it's 1:5, then 5:10, and then 10:10, and then 10:5, and then 5:1. And for sextuplet, it's 1:6, then 6:15, then 15:20, then 20:15, and 15:6, and 6:1. So this is the Pascal's triangle that one should remember in order to find out the multiplicity pattern, that what will be the intensity for the doublet. So doublet will have, singlet will be this, doublet will be 2 lines of equal intensity, triplet will be 1 line of twice big as 2 lines. So this is the triplet, and the quartet will be 2 lines bigger and 2 lines smaller, right? These are the multiplicity of signals that you can understand through that Pascal's triangle. So in this video, we have learned about coupling and multiplicity, and we have learned about the Pascal's triangle. We will make I'll make more videos about NMR spectroscopy following the Clayden book first, and then I'll follow the Pavia's book. Keep watching this channel. Thank you and take care. Bye.